Well, we've been discussing light for some time, and we're going to get a little more practical. We're going to migrate toward mirrors and lenses and understand how they work. But just some preliminary stuff, some time delay repetition, perhaps, and a little new information. How do we see light? Well, we see it directly from a source, like when we look at the sun, or a candle, or a flashlight. Or it might be reflected by an object. And reflections are just a secondary effect. A source shines on it and reflects those wavelengths that aren't absorbed by the pigments that the object has. And our experience tells us that light travels, well, in straight lines. Because we've never seen evidence for it going around a corner, right? Okay, it's kind of intuitive. It may not necessarily even be true, but intuitively it is. So we often consider light as being a ray that moves in straight line paths. And we've modeled it this way already, so I just want to reconfirm that. We're talking about a ray is an extremely narrow beam of light. Infinitesimally narrow, you could say. And light is really an electromagnetic wave. Of course, it's also photons. But considering them as rays is useful for our models that we'll build to understand reflection, refraction, and then where we're going toward here, the formation of images by mirrors and lenses. So that will be useful. So we're going to stick with the ray idea here for a while. Now, when light hits an object, it's either reflected, and there's actually two types of reflection. In any case, at any point, it obeys the law of reflection. So if we put a normal here, the incident and reflected angles are the same with respect to the normal. It might be absorbed, which just means it's converted to other types of energy. So here's a ray coming in, has some light energy, and it kind of fizzles out. And maybe goes out with a bang, but I'm not sure when that happens. Probably usually not. A little bit dramatic there, I guess. And it might be transmitted. Plenty of examples of that. Glass or plastic or water, where the light transmits through. So let's consider reflection a little bit more. Reflection. So we have a surface, and we have an incident ray striking the surface, and there's an incident angle with respect to the normal. And when an incident ray strikes that surface, it bounces off at the same angle with respect to the normal. So that is the basic law of reflection. Theta incident is theta reflection. So the law of reflection, which you're familiar with already, the angle of incidence equals the angle of reflection. There it is. Very important. And it's always measured with respect to the normal. Now, I mentioned there's two types of reflections, and the first one I want to consider is diffuse. Light is reflected in many directions. Most objects have this. And there's really clear evidence for it. Namely, if you shine a ray of light on a surface, even if it doesn't bounce directly into your eyes, like here, you shine this, even if your eyeball isn't right here, maybe your eyeball is over here. Do you still see the spot of light down there? Usually the answer is yes. And if it's yes, that means photons or waves of light energy came to your eyeball. And put your eyeball anywhere else, and you probably will notice the same thing. So we're going to consider a rough surface. And there's a ray, and there's how it bounces. But either, in practical terms, that ray of light, if it has some spatial extent like a laser beam, there's a region over which it's impacting the surface, not a infinitesimal point. But consider a variety of infinitesimal points. At each one, the surface, because it's a little bit rough, has a different angle. So it's obeying the law of reflection at both of those points, but it's not all, the normal isn't uniformly perpendicular to what the big picture looks like here. Okay, that makes sense. So another part of the ray, or another ray, or part of the extended beam of light coming in, we see that there are a variety of possible angles at which the light will reflect. It's obeying the law of reflection everywhere. But you see it at all the angles as long as it's above the plane. I mean, you wouldn't expect to see light underneath here. But if you're shining like this, and this is opaque, then anywhere you put your eyeball in here, go to anywhere and you're going to see that light, which is direct evidence that the reflected angles cover the spectrum here as long as it's above the plane. So every microscopic point, the law of reflection is obeyed. If you think about it, that's really amazing, because you can't find an angle, usually in a practical sense, you can't find an angle where you don't see that little spot of light. So that tells you that all the angles are represented. And so now the other kind of reflection is specular. So we have diffuse and specular. With specular, light's reflected in one direction. Corresponds to an ideally smooth surface across its entire expanse. So here's all those little microscopic rays coming in, and we have a single normal, and they all bounce off at the reflected angle, which is the same as the incident angle as before. It's just that now the normal is in the same direction. In other words, the normal is the same for every single one of these. Okay, so we see the light over this region here. We don't see it over here, and we don't see it over here either. So light is seen at only one angle, which is the angle of incidence, or the angle of reflection, which is the same as the angle of incidence. And again, that reflection is obeyed at every single point, just all the same. So specular reflections now give us the opportunity to understand, perhaps for the first time or for review, how a mirror works. So why do you see the image that you see in a mirror? Let's bring out our baby of physics. This is our baby of physics, and it's a contemplative little baby, as you can see by the large head and the finger up to the chin or to the cheek, showing that it is in a reflective mood at this moment. Ha ha ha. So anyway, here's a plain mirror on edge, so we don't see the surface, it's just the edge of it. The baby's looking at the mirror, and we're going to define the distance to the object, namely the baby. There it is. And now we're going to put our eyeball here. We're going to look. Now, when we see that baby, do we see the baby when we look in the mirror? Now, you can probably answer the question just from your experience. I suspect you would answer yes. You would see the baby. And you would say, why? Because the baby's image is reflected off the mirror and hits the eyeball, right? That's pretty good, but let's make sure we understand. So here's a ray of light coming from the top of the baby's head. Now, I hope you'll agree that no matter where you are, you could look directly at the head and see photons of light or rays of light coming from the head, no matter where, well, not behind here, but anywhere you put your eyeball, you're going to see the top of the head. But that means that rays of light from the top of the head are going every direction, including the direction I'm showing here. This particular direction is a solution for all the directions, okay? And since this is a smooth surface, it's going to obey the law of reflection. The reflected angle is going to be the same as the incident, and that's the ray that takes us to the top of the eyeball here. Now, the person is observing this, and they don't know that the light originally came from here. They think, the perception of the brain is that the object is in reverse direction of where the light came from, so we're going to project back like this. And to figure out where exactly this is going to be, we're going to do another ray. This particular ray is also reflecting to the eyeball, but on the bottom of the eyeball. So everywhere in this range here, the eyeball is picking up rays of light coming from the top of the baby's head. This latter one projects back like this. And at the convergent point is where the person sees the top of the head. Let's do the foot. So there's the bottom of the foot, and there's a ray that enters the eyeball. Projected back is there. Another ray, this particular one, and every one in between is at the other end of the eye. Projected back, the observer thinks it converges at this location. And we can do that for every other point on the surface of the baby. And guess what? You form an image of the baby. All right, there it is. That's what you think you see. You see it. Now, do you see it in front of the mirror or behind the mirror? You see it behind the mirror. Isn't that something? This is the distance to the image. Little definition there. Now, the rays, you see it behind the image, right? The rays do not actually pass through the image location. In other words, here's the image, but the rays of light are really bouncing off of here and going to the eyeball. No rays of light are ever back here. In fact, this might be a concrete wall back here. There's no rays of light there. So the image formed is either real or it's virtual. And having said what I said, I'm sure that if you were challenged to answer that correctly, you would correctly name it virtual. It's not real rays of light that pass through it. It's a virtual image. And by similar triangles, we can deduce that distance to the object is equal to distance to the image. The image produced by a plane mirror, flat mirror, is always virtual. To get just a wee bit more insight into mirrors, plane mirrors, let's consider how much of a mirror is needed to see your full image. Oh my gosh, that guy's kind of crazy. So is a full-length mirror necessary to see oneself completely? You know, does it need to be as tall as you are?
What?
Yeah, don't worry. You are obviously very clueless, but you don't have to know because we're going to determine this for you. Because we know physics and we can draw rays. And we're going to start with a ray coming from the base of the foot of this clown. And it's chosen in such a direction to obey the law of reflection and go to the eyeball. Very good. Project that back. That's where this guy sees the bottom of his foot. Likewise, top of his head. I think bottom of the foot to top of his head spans the whole height. So obeying the law of reflection, and that hits the eyeball. So project that back, and there it is. And the image. So this region here is the full extent of what is needed to see all of oneself. So the answer is no. It appears that if you look at this much is needed, this much is left off, and so is this. How much is that? A third, a quarter? How about a half? Looks like about half is needed, right? Let's do this now. Let's take that way back, take a few steps back, and I've eliminated the part of the mirror. We've only got this much of a mirror now. This is just, blocked with paper or something. Let's see how much of his image disappears when he steps back. So we'll just do the same thing again. Bottom of the foot, at the base of this, and that reflects to the eyeball. Projects back like this. Top of the head, at the other end of the mirror, bounces off into the eyeball, projects back, and guess what? It's all there still. The whole image is there. So what we've just demonstrated graphically here, even though these angles are different, it all kind of is, you could say, everything is proportional in terms of how this works. And the object distance then has no bearing on the amount of the image that's visible. But we did see that we don't need the whole thing. Now, so that's the basic idea for a flat mirror, but now it's time to get into curved mirrors. What if the surfaces are not flat? So we have concave, which means the center of the mirror is further away than the edges. Kind of looks like that. See, this is further away from the person than the edges. The edges are closer. Or convex, the center of the mirror is closer than the edges. So that's just the opposite. Flip it around. And you're over here, and the center is closer than the edges. So let's, in our next lesson, start to investigate what happens to an image when we have concave or convex mirrors.